Good morning, ladies and gentlemen. This is Ben Keyser with Applied Flow Technology. I hope that you are all doing well and having a good week so far. And I will apologize in advance. I am working really hard on trying to get over a cold. So thank you for listening in today's webinar. And just please bear with me as we get through this. And if all of a sudden you hear my sound go silent, don't panic. That just probably means that I'm trying to mute myself to rehydrate and keep my throat from getting dry. And so just wait a few seconds and then I'll be back online. So bear with me and we'll get through the webinar. So I was having troubles trying to upload the PDFs that I wanted to share with you all in the handouts. So for those of you who are listening in live, this webinar is being recorded as usual. Please email me at benkeiser@aft.com. That's BENKEISER @aft.com. And I'll be happy to send you the PDF of my presentation. And for those of you who are listening to the recording, same thing goes there. Feel free to email me at BENKEISER@aft.com and I'll send you a copy of the presentation. So if you had listened in on a webinar, it was probably a year ago, July 2018, I did a webinar on dust collection systems, and I actually provided a link on where you can find that. So when you email me, I'll send you my presentation. This is a direct link to the webinar that you can watch that I did on dust collection systems back in 2018. And that was a webinar that I went through and I discussed guidelines for dust collection systems, things that are important in regards to guidelines and applicable codes and standards, and why it's really important to model a dust collection system and how you can model it with AFT Arrow. And so the webinar that I'm doing today is going to build off of that. I'm going to show you how you can use the new AFT Arrow ANS module to help you automatically meet your design requirements. That's the automated network sizing module. And so if you're not familiar with our software products, then you can go to our website, aft.com, and then under products, you can go to the software overview. And this is where you can learn about all of our different software tools themselves. And this is the one that we're going to be talking about today, AFT Arrow. And then when you pick one of the products that you want to learn more information about, then you can scroll down near the bottom, and this is where you can click on to learn more information about the automated network sizing module and what it will do and how it will benefit you. And so that's what we're discussing today. So let me get back into this. So here's what the agenda looks like. I'm going to revisit the previous dust collection system example that I did in the webinar a year ago. And I'm going to also summarize the guidelines that I presented last time for the dust collection system setup. We'll go through and take a look at the model results based upon the guidelines that I built the model of for that system. And then we're going to use AFT Arrow to automatically size the ducting system, and how even this is going to demonstrate how even standards and guidelines of various rules of thumb for your design just still will not always get the job done properly. And very well could be that it's impossible design for the system to be able to function thermodynamically. And that's what AFT Arrow will demonstrate potentially. And so rather than using the various rules of thumb methods for guessing and checking, AFT Arrow's ANS module will intelligently determine the pipe sizes for you that you're going to need to use. And so we're going to apply that to the previous example that we did. So again, this is where you can find the link to the webinar on dust collection I did last year. It addresses basic issues and standards regarding dust collection systems. I talked about basic guidelines, built an AFT Arrow model, and then if you remember, if you watched that webinar, the AFT Arrow model actually demonstrated that the requirements were not met from the guidelines. I'm going to show you that again today. So before I get into this, I want to really quick show you something in AFT Arrow, because this webinar was intended to talk about ducting systems for AFT Arrow. And so you can easily model ducting systems with a regular pipe. You just draw it on the workspace. And if you select that pipe and open up the property window, here's where you can change it to a rectangular duct, is the pipe geometry. So if you change that drop-down menu to rectangular duct instead, then this is what allows you to specify the duct width and the duct height. Again, remember that blue highlighting represents required input. So wherever you see blue highlighting, that's input that you have to specify. So if I go in here and I specify a 6-inch width and a 3-inch height, then it's going to calculate a hydraulic diameter of 4 inches. And that's what's going to be used for the calculation. So specifying rectangular ducts is as easy as that. Incidentally, AFT Arrow does have a rectangular duct database built in that you can use. So you would choose pipe material, rectangular duct, AFT customary, and these are various sizes that we probably got from a handbook somewhere. And so, or maybe a manufacturer's website. I can't remember off the top of my head. But anyway, you would go through and select the size as well as the type. There's different gauges available, and then that'll populate the appropriate sizes for you. So it speeds up the definition process significantly. Now, when you're dealing with the ANS module for sizing your piping systems, you're going to be dealing a lot with databases. And knowing how to use databases is going to be critical, and it will make life actually a lot easier for you. So one thing I want to point out on our website is our tips and tricks area. If you go to AFT.com, under the Learning Center, there's a tips and tricks area, and this is where we write blogs of really important modeling concepts, and there's tons of them there that will help you learn more effective and efficient ways on how to use the software. So if you click on the magnifying glass here to search and do a keyword search simply for the word databases, you're going to find a 4-part blog series that I wrote a couple years ago, well, I guess a few years ago. Databases 101, fluid databases, pipe material databases, and how to share databases. It's meant to be read in this particular order. That's why I did 101, 201, 301, 401. But the specific database that talks about how to build your own custom pipe materials is this one right here. Databases 301, those are some nice pipes. So you can also apply that for rectangular ducting systems as well. A lot of times it's so much easier to build your custom database in a spreadsheet and then simply import it in to AFT Arrow. So here's how you would do that. You go to database and then pipe material database. And once this opens up here, what I want to click on is import from file. If you click on import from file, this is going to bring up a window that tells you the structure that your spreadsheet or your CSV file needs to be in order to import all that data into a new custom database. So what you would do is same thing. You would click on the geometry drop down and you would change that to rectangular duct. So now you can see how the menu of items changes. So what you would need to specify in your spreadsheet is multiple columns. In column 1, you'd have your material name, nominal size, type, duct width, duct height, and wall thickness. And so when you specify your spreadsheet, you can easily generate hundreds of rows of data of different duct sizes, and then you can import that right in as a custom pipe material database, which you can then use for the automated network sizing process with ANS. So that's really important to become familiar with. And if you haven't learned how to use databases yet, please be sure to read those 2 blog articles, and you'll be up to snuff with how to use them very quickly. Okay, back to the presentation here. Give me 1 second. Okay, excuse me. So here's the dust collection system example that I demonstrated in the previous webinar. This is a wood manufacturing system, very generic. We've got a table saw, a lathe, a radial saw, a floor sweep, and a sander. And then this is where our dust collector is. So that's a typical diagram of a dust collecting system. This is the plan view that shows a little bit more information on the relative layout of where all the components are in the system. Now, the important thing here is that when we were doing this model last time, we only knew what the layout was. The example that I got this from did not say any information about what the ducting lengths should be, what the elevations were. So the previous ducting sizes that it generates here, these are sizes that are based upon the rules of thumb that the resource outlines, which I'm going to show you here in just a second. So those are assumed sizes that were calculated during the rule of thumb guideline, whatever you call it, sizing process. Very rudimentary. So what ANS will do is it's going to determine the duct size for you. And here's where the reference you can find for this particular example. So if you go to this website, airhand.com, then it'll pull up their website, and there's a lot of really good information here about dust collection systems. I highlighted it in the previous webinar, and you'll be able to find the reference guide that talked about all the various design considerations for a dust collection system. So some of the basics regarding dust collection design is the duct velocity. The fluid velocity has to be fast enough in order to carry the particles through the ducting work. And so there are different velocities for different kinds of dust that you might be working with. And so these are just some very general guidelines. It typically requires that you have a higher velocity in the side branches, but doesn't need as high of a velocity in the larger main ducts as well. So those are the velocity requirements. You would determine your branch sizes based upon the size of or the type of equipment to the main duct header. These are some flow requirements in cubic feet per minute, and based upon the velocity that you need and the flow that you require, that determines what your ducting size is going to be. So it just comes right off the chart here. Now, again, one of the things that AFT Arrow demonstrated is that this chart is just, it's not good enough, because even with these rules of thumb, your system is just a lot of times not going to meet these requirements. And so that's where you need to have a more intelligent design rather than just reading things off of rules of thumb and charts like this. So an example is we need 350 cubic feet per minute for the table saw for woodworking dust. So woodworking dust, we would need 4,000 feet per minute, and then 350. So the table saw duct size would be 4 inches in diameter. All right, let me erase that drawing there. And then these are the primary machines that we have operating: the table saw, the lathe, the radial saw, etc. Again, watch that webinar, and I went through all those details of what all this stuff means here. And so I'm going to skip it. I'm going to jump into the Arrow model now. So this is the Arrow model that I built of that system, of what I thought it might look like. And the assumptions that I made were on the ducting lengths, the elevation, and then for the elbows that are in the pipe duct runs, I modeled those with K factors. And I used either a 90-degree elbow or a 45-degree elbow accordingly. Now, one of the other things I didn't mention that was an assumption was I'm using round steel ANSI cylindrical pipe duct work. So this is actually regular steel piping that you probably wouldn't use for your dusting collection system, but I just kept it simple and used steel pipe. So this is my Arrow model, and I'm going to go ahead and jump into that model right now. So give me one moment here. Sorry about that, I had to mute myself. All right, so all right, let me drop back to the base scenario first here. So here's my base scenario. This contains all the same input that I showed you on this particular slide right here. So this is all the same input information. I just kind of moved around some of the pipes and junctions a little bit, and then I added some names for the various branch lines and header lines. That way I would be able to make it a little bit more clear for myself when I was looking at the results. So in order to know if our design requirements were met, using standard AFT Arrow, you could do this easily with creating design alerts. That's exactly what I did. So under the Tools menu, if you go to the Design Alerts area, this is where you can easily define various minimum and maximum values for parameters in your systems. So the way that you would create a new design alert is just click on Create a New Design Alert. You can do design alerts for both pipes and junctions. And then you specify your parameter, whether it's a maximum or minimum value, give it a value, and then specify which pipes or junctions that it applies to, and there you go. That's all there is to it. Sorry about that. So I already went through and created 4 design alerts. So my first design alert is the minimum branch velocity. So I need to ensure that the velocities in my branch flow paths right here, those need to be having velocities higher than 4,000 feet per minute. So that's my primary branch minimum velocity that I need to achieve. The next design alert was the minimum duct velocities. So in the main duct header, which would be this pipe here, and then this group of piping that leads to the dust collector, those header pipes have to maintain velocities higher than 3,500 feet per minute. And that's to be able to carry the particles of the given woodworking size. And then finally, I have design alerts for the flow rates in some of the ducting parts of the system. So the table saw and the lathe, that's these two flow paths right here. Those require 350 cubic feet per minute through each of those flow paths. And then the radial saw, which simply applies to these two pipes right here, that requires 550 cubic feet per minute. Excuse me. All right. So this is what you would be doing if you were using standard Arrow to help you with your design. You would follow the guidelines and the rules of thumb of these various design processes. You would build your system, and then you would use pipe sizes that it specified based upon those rules of thumb. And then you would run your model and check to see if your design requirements are met by using the design alerts. So let's go ahead and run the model and see what we got. Well, as you can see, I've got tons of design alert violations. So that's what the big red warning messages are telling us right here. Now, what I'm going to do is I'm going to move the output to the right-hand side. That way, it's a little bit easier to pinpoint where these messages are referring to. So let's break this down. Let's look at the first one. Velocity is below the minimum design alert of 4,000 feet per minute for pipe 1 at the inlet and at the outlet. So here's pipe 1, the inlet and the outlet. The velocity is less than 4,000 feet per minute. So if I look in my output table, wow, that's really low, 1,300 feet per minute. So I'm not even getting anywhere near the minimum velocity that I need in order to carry the dust particles. Same thing in the rest of the flow paths as well. And as you can see, it's going to highlight all of those violations for me in the output table. So that is what I see for the table saw line. And then we can also take a look at some of the other design alerts here for flow requirements as well. So if I scroll over, I required 350 cubic feet per minute through each of these flow paths here and then for the lathe. And as you can see, we're not even getting anywhere close to that 350 cubic feet per minute. So what this is telling you is that those design rules of thumb are just, you can throw them out the door. I mean, there's so many cases where they are just not going to do the job for you. So this is where having a tool like the automated network sizing module is extremely beneficial, because it'll automatically take into account all of your design requirements, and it'll adjust the pipe sizes or the ducting sizes as necessary to meet those requirements. So this was the first scenario that we did last time in the previous webinar, and this just highlights how the design is not going to work. So I'm going to put that output window back, and we're going to go on to the next scenario here. So the next scenario is my ANS test scenario. Now, one of the things that the link to the rules of thumb on dust collection design contains is that it told you that, you know, when you're sizing your system, you're only sizing it based upon the main pieces of equipment operating at the same time. So it's assuming that I only have my table saw, my lathe, and the radial saw operating. Floor sweep and the sander are not operating at that time. So this is another major downfall to these rules of thumb, is they dramatically oversimplify the process of what's actually happening. You know, who's to say that it's guaranteed that these two pieces of equipment are always going to be turned off when the rest of these are running? So when you're designing your system, you want to design for the case of where you need the maximum amount of flow. That way, if you had the maximum amount of flow going on, then at least your design requirements would be able to be met in those cases. So that's what I'm doing right here for the ANS sizing, is I have set the floor sweep and the sander lines to be on and active, and all of the paths are supplying flow to the dust collector. Give me 1 second here. Excuse me. All right. So first things first, how do you turn on the automated network sizing module? Well, there's a couple ways. One way is in the quick access panel. If you go to the button just to the left of the status light, you click on that button, and this is where you can check the box, turn on the ANS module. If you have a license for the ANS module, you'll be able to access that capability, and then it'll be turned on for you. The other area is to go to the Tools menu, activate modules, and check the box. The main thing here is that your add-on modules do not require a separate installation. When you install AFT Arrow, the add-on modules are installed with it. Once you have a license available, that will access the capabilities. Excuse me. Okay, so now that I have turned on the automated network sizing module, you'll see that there's a new primary window tab up above. That's our sizing panel. That's where all the magic happens for the sizing process. So let's break this down. When you're going through the sizing process, there are several steps that you need to take along the way. And you can you can do any of these steps in any order, but it's easiest to complete them by going from left to right. Now, this already has everything already set up. I'm not going to go through the process of setting everything up from scratch, but even though it looks like there's a lot of steps, it's really not that hard. It's very quick and simple. So here's what we're dealing with. Let's talk about the first option right here, the sizing objective. So this is the sizing objective panel where you need to do a couple of things. First thing, you need to specify if you're going to size your system. That's the first option, is to actually change your pipe size. That's what the ANS module is for. However, the middle option is to calculate the piping weight, do not size. Well, what that would do is if you have a current and existing design and you just want to know how much that costs, you can run the regular Arrow simulation. It's not going to change the pipe sizes, but based upon the defined pipe sizes that you already have, it's going to calculate the overall piping weight or the overall cost for that system. That is similar to a cost calculation example run that you would do with AFT Arrow. And then finally, the last option is to do not size. Well, why would you use this option? Well, maybe you go through the process and you set up all of the different options here and you have defined all your design requirements, but you just want to run your model really quick to see what's going on, and you don't want to deal with any of the sizing, and you don't want to lose all of that input information you already specified. Well, if you do not size, you can just do a regular Arrow run. That way it does not delete any of the information that you already specified. So it's a really convenient way to run your model and ignore all the sizing data without having to delete it. So in this example here, we want to perform the sizing. So once you pick which option you're doing, we're performing the sizing, you'd have to specify an objective. What's your goal? You know, when you're sizing your pipes, what are you trying to do? Well, we want to minimize cost, okay? That's the best way to size your pipes, is to try and minimize the cost. If you have monetary cost information, such as material and installation cost for piping and junctions, and maybe you have energy cost for operating your compressors and fans, then that's where you can use the monetary cost. This is going to be the most detailed option, and it's going to be the most accurate, because when you're taking into account actual costs for your system, then it's going to give you a much more accurate, detailed design for your pipe sizes that you actually need. Now here, in this example, I don't know any monetary cost information. But one thing I want to point out here is, as you can see, when I selected monetary cost, it did turn on this panel right here to assign cost databases. So what this is telling me is, if I'm going to use monetary cost information, there's some more input that I'm going to have to specify. Not a lot, but a little bit. Now, if you don't have any monetary cost information, then the best thing to do would just be to simply minimize the overall piping weight. If you minimize the overall piping weight, typically that's going to track really well with minimizing the initial cost. So if you minimize your piping weight, you're minimizing your initial cost, and that's a really good way of being able to size your system. So it's the simplest way to go through the sizing process. So that's what I'm going to use here, is to minimize the piping weight. Let's move on to the next one, sizing assignments. The first step that you need to do is, for all of the pipes in your system, you need to specify if they are allowed to be sized or if they're going to remain the same size that you already specified. Okay, so if this is an existing system where my pipe sizes are not allowed to change, then I would not use these two columns. I would use this column right here, where all my pipes would not be sized. They're going to stay the same size that they are. However, I might want to know how much they cost or how much they weigh. So that's where I could use this column as well. So that's one option. The other option is, let's say that you have an existing system. Let me go back to the workspace real quick here. So let's say that the only things that are new are the floor sweep and the sander line. Everything else is already there and is operational. So if my two new flow paths are the sander line and the floor sweep, those might be the only pipes that I want to change the size for. So when I go back to the sizing panel, those groups of pipes are what I would use to be sized, but then we have other pipes in the network as well. Let's say that I want to consider potential changes in the main ducting header. So if everything else is already operational, but if I want to say, well, for these ducting piping that I have already laid out, if I'm able to find a better design where I can change the duct size, I'll consider it. So if you have that type of flexibility to where you can consider pipes that might change, if you can find a better design during the sizing process, then that's what this column is for right here. It's where you have piping that's already there, which would not necessarily be allowed to change, but if you have the flexibility to change out some pipes, where if ANS can find some better designs, then that would potentially allow some pipes to maybe change. So that's what you would do first, is you would specify which of your pipes are going to either be sized or not sized. This is a brand new system, so we're going to allow everything to have their pipe size changed. So that's the first step. The next step is to create some common size groups. So when you are looking at your system here, back on the workspace, there are 21 different pipes on the workspace. That's what that little icon means down in the bottom right corner. You have 21 pipes. So if I did not create any common size groups, the Arrow ANS module could potentially determine a different pipe size for every single duct in this system. And that's perfectly fine, but it's going to make purchasing really difficult because it's 21 different sizes that you have to deal with, and it's just not very practical. So when you're sizing your system, you're probably going to want to maintain some level of commonality throughout your network. So maybe this group of pipes will be a certain size. This group of pipes could be a different size. Maybe this group of piping can be a different size, so on and so forth. That's what the common size groups are. So that's what I already did was I clicked on new. You give your sizing group a name, click OK. And then what's really easy is if you move if you move the sizing panel over to the right-hand side, this is where you can quickly assign specific pipes to certain groups. So you can select them on the workspace first. Once they're selected on the workspace, click on Workspace. Let me highlight that button for you. So I clicked on Workspace. What that does is it selects the rows for those particular pipes. So if I want to move those groups of pipes that are selected over to this common size group right here, all I would need to do is click on Move To and then Group 1. And there we go. Whoops. That's how you can easily specify which pipes are going to be in which common size groups. Now, obviously, this is not what I want to do for those specific pipes. So I'm going to move them back. So I click on Workspace. It highlights those rows again. And I want to move these back to the table saw line common size group. So I just click on this drop down, move to table saw line, and there we go. That's all there is to it. Now I'm going to go ahead and delete my group 1. Whoops. Let me scroll over again here. So delete group 1. I don't need group 1. Okay. So that's what I did for all of the common size groups. I selected the pipes on the workspace. I clicked Workspace. And then after I created my common size group, I went to Move To Lathe Line, and then bam. That's how these pipes got there. And then I did the same thing for the radial saw line. That was just these two pipes, and they're right there. And then we've got the floor sweep, we have the sander, the blower header, etc. Now there are some pipes that are not in a common size group. That's perfectly fine. So those 3 pipes that are not in a common size group, they are the header, which is the table saw plus the lathe. That's this particular pipe. And then there's the header with the table saw, lathe, and radial saw. That's this pipe right here. That's where after these 3 branches has added together. And then finally, I have P14. That's this pipe right here. And so that's the header with the table saw, lathe, radial saw, and floor sweep. So those do not have to be in a common size group. Now what this will do is these could all potentially be different sizes in my header. So they could all be different ducting sizes, and that's perfectly fine. However, if you want to force them to be the same, then all you would need to do is just create a common size group, maybe call it header, and then they can be in the same common size group. When you add more pipes to various common size groups, what that does is it decreases the number of independent variables. So that's making it easier for the solver to be able to find a solution for you for some better commonality. If you have more variables, it's going to be more calculation time. It can still do it, but when you reduce the amount of independent variables, it simplifies the equations that are being solved. So that's a really important reason on why you'd want to use common size groups. All right, I'm just trying to make it through the best I can here. Thank you all for bearing with me. Next step is candidate sets. So once you've gone through and you've specified your common size groups and which pipes are allowed to have their size be changed, you have to pick pipe materials that you can use to change the pipe sizes to. Give me 1 second here. Okay, so what you would do is you would click on New, and you give it a new name, New Ducting Material. And then this is where you would select a specific pipe material database that you want to allow as choices to be selected for sizing your system. So let's say I did rectangular duct, and if I do standard sorting, this sorts everything by size, and then you'll find multiple types within each size. An easier way is to maybe sort it by type. So maybe I only want to consider 24 gauge. Well, these are all the sizes that are available in 24 gauge. So if I select the 24 gauge level and then click on Add, that's going to add all of the ducting sizes that are 24 gauge. And so when AFT Arrow ANS module does the sizing process, these are the potential pipe sizes that it's going to select from to try and figure out which pipe sizes are the best to use for my system. So that's how you set up what's called a candidate set. It's the candidate, or it's the list of choices of pipe material that you can use for the sizing process. So here I'm using steel ANSI piping, and I'm using, looks like a whole bunch of different schedules. After you specify your candidate sets that can be used, you would you would assign specific candidate sets to different common size groups. Now, it just happens to be that I'm only using steel piping here, and I'm using that for all of the pipes in this entire network. However, if I wanted to create multiple candidate sets like the rectangular ducting or copper or PVC, whatever I wanted, that's where you can do different types of materials, different sets of materials for different common size groups. So there's a lot of flexibility that you have there on allowing which materials can be used for the sizing process. The next step is the design requirements. So this is what's going to drive my design. These are the same design requirements that I used before, where I had my minimum velocities. And as you can see, the minimum velocities in the branches has to be 4,000 feet per minute. And then in the main ducting headers, I need 3,500 feet per minute. So that's velocity, and it's just overall velocity. Inlet, outlet, inside the pipe, any velocity, it has to be above those minimums. Secondly, I have my flow requirements. So the minimum flow from the table saw and the lathe, that requires a minimum flow of 350 cubic feet per minute, while the radial saw requires 550 cubic feet per minute. So once you create the design requirements, the next step is to specify which requirements go with which common size groups. So here I have my minimum primary branch velocities. That's my first design requirement right here, row 1. So this row 1 applies to the table saw common size group. It also applies, let me expand this down here. It also applies to the lathe line and the radial saw line. Now, if you click on the main box here, that will check all the boxes for you, but you can check and uncheck the boxes individually if you want. But watch what happens. If I uncheck that, it unchecks it for everyone. If I recheck it, it checks it for all of them, and then you can uncheck them accordingly. So that's the minimum branch velocities that I need. Then I also have minimum duct velocities. So this is the main ducting after the sander, which is the blower, that common size group. And then I'm also assigning the same design requirement to the 3 header pipes, which are not in a common size group. and then so on and so forth. So it actually is possible to have multiple design requirements for the same common size group. So if you look at this, the table saw line, it has velocity requirements as well as flow requirements. So you can do as many different design requirements as you want, and you can apply multiple design requirements to the same common size groups, and that's perfectly fine. Now, what you'll find is that some design requirements actually matter in dictating what pipe size you need to use. Some don't. Maybe you've got a minimum pressure requirement that you need to meet. Well, you know, if it's just going to meet that design requirement naturally to where pressure doesn't matter, no matter what size you use, then that would be a inactive design requirement. Now, I'm not going to talk more information about what that means. That's a little bit more detailed, but some design requirements may not matter. So these are design requirements for pipes. You can do design requirements for fans. Maybe I've got a certain efficiency of my fan that I want to meet, or for like Fathom ANS, maybe MPSH for your pump is a certain goal that you want to be able to meet. And then you can do different design requirements for general junctions as well. So that's all my design requirements. That's all set up. The last thing is to specify my sizing method. There's different sizing methods available, and there's two ways that you can size your pipes: continuous and discrete. Continuous means that it's going to find any inner hydraulic diameter that will be able to meet your design requirements. So it's possible that your overall duct size could be 17.37 inches in diameter. Well, that's not typically a standard size that you're going to be able to go down and buy. So that's where it's important to do discrete sizing. Discrete sizing is only going to consider pipe sizes in the list of the candidate sets that you specify. That way, it'll ensure that the diameters that you need to meet your design requirements can be purchased as standard materials. So that's what the discrete sizing option means, and that's the best way to size your system. Now, one other comment that I want to make is that there are 4 different methods currently on the algorithms that you can use to size your system. These are very, very powerful optimization methods that are built in to determine the best combination of pipe sizes for your system in order to minimize your objective, which in this case is piping weight. So the thing is, if you're switching between different mathematical methods, it is possible that each of them could come up with a slightly different design. Well, that is going to impact things potentially. Which design would you use if each of them comes up with slightly different sizes? Pick the one that gives you the lowest cost. Let's say also that the current pipe size I'm using for the initial input, that could also potentially make an impact on design. So if I'm using different sizes versus making everything be 12 inches in diameter, where you start your initial pipe size guess in the model input, that could potentially have an impact on what your resulting pipe sizes might be. So the moral of the story is, when you start using this, you're just going to have to play around with these different methods a little bit to get familiar with them. If you read the help file, it's going to give you a lot more discussions regarding each of the different searching methods. So what you can start with is suggest the best method and then go from there. So let's give it a shot. So we're going to run our sizing process. What it's doing is it's going to calculate the cost of the initial design. So this is the cost of my initial design with the model input that I specified from the beginning. Again, that's not necessarily the real pipe size that it's going to use. It's just a starting point. And as you can see, the initial design is infeasible. That means that my design requirements were violated. It's not able to meet the various velocity or flow requirements based upon the given pipe size, and this is how much that system would cost in terms of the piping weight. After it does that, even if you select discrete sizing, it's going to do a continuous sizing operation first. The reason why it does a continuous sizing is because it tries to come up with a better starting point before it does the discrete sizing. So it goes through and it starts to figure out just regular hydraulic diameter, and it calculates a certain cost, and it gives you a little bit of information about how long it took to get there. And once it found the continuous cost, it then performed the discrete sizing. So now that the simulation is converged, let's go and take a look at our resulting pipe sizes. So if we go to the output window here, let's take a look at the cost report. The cost report is going to give me a breakdown on how much each individual pipe costs. In this case, since we're trying to minimize the piping weight, this is how much each pipe weighs in terms of pounds mass. And so the total weight of the system is just under 4,000 pounds. So that's by using the sizing by weight. If I had used a monetary cost objective, when I set it up here, then you would see a more detailed breakdown. You would see how much it costs for material, installation, maintenance, and energy for each pipe in your system. You can also include fittings and losses, and it'll calculate those costs as well. So that's the cost report. That's really helpful because that tells us how much it's going to be. That will help us establish our savings. Then if we look at the pipes tab here, there's a new tab. There's sizing. So when we look at the sizing here, I included the names that I created for all of the pipelines, and you can see the original pipe sizes that I was using. So these are the original pipe sizes that I was using, and then these are the sized pipe sizes. Now, for the table saw, it found that it did not need to actually change the size. Maybe it needed to change the size elsewhere in the system to where 4-inch diameter for the table saw could still work and meet my design requirements. Now, there's these groups of pipes right here, which are saying that the size is unavailable. What this means is that it found a hydraulic diameter that would be able to meet the design requirements, but I did not have a nominal size in my candidate sets that was close enough to be able to meet the hydraulic diameter. So that's why it's telling me this is what the sized hydraulic diameter would be, but it was not able to find an appropriate candidate set pipe that met that operation. And then finally, look at this, when we thought the floor sweep needed a 5-inch duct size, it only needs 2 inches. The sander, same thing. We thought it needed 4-inch, it only needs 2. So this just goes to show you where the rudimentary rules of thumb and guidelines of those various design practices just very well may not get the job done. Still perfectly fine to use the design requirements because that's what's going to carry our flows through the system, but the sizes could be very different than what the rules of thumb might come up with. So this is where it's really important to let Arrow do it for you, because Arrow will do it intelligently versus just reading off rules of thumb. Arrow can potentially help you find a much better design that will work a lot more effectively. So here, these are all of these summaries of the design requirements. I'm going to maximize this window here. So here are the design requirements for my minimum velocity of 4,000 feet per minute. As you can see here, these 4 pipes right here, those are the pipes for the table saw line. So these pipes are highlighted in yellow because this design requirement actually drove the design for those particular pipes. However, if you look at pipes 6 and 7 and 9 and 10, which were the lathe line as well as the radial saw line, well, based upon the flows in those paths, the velocities were very well above my 4,000 feet per minute. So it was a design requirement, but it didn't even matter because it was going to meet that design requirement anyway. So the yellow means that that was an active design requirement that drove the design for the discrete sizing process. The blue means that that was a design requirement that was driving the design for the continuous process. So when it was going through and just trying to find any hydraulic diameter that worked, the blue meant that those were very, very close to the 350 cubic foot per minute minimum, and that drove the design for a certain size. But then once the discrete sizing process took over, then they were not active design requirements anymore. Only the requirements in these groups of pipes really mattered in driving the design. All right, so really that's all there is to it. The visual report, you would be able to show both your sized pipe as well as your original pipe size. So here's my original pipe nominal size, and then my sized pipe nominal size. And that way you can see right on the workspace how things are actually different. So we got 4-inch and 4-inch, but here, looking for another pipe. This pipe we thought we needed 4-inch. Well, for that header, we actually only need a 2-inch diameter header. How about that? All right. Well, that completes today's webinar on how you would be able to use AFT Arrow's ANS module for doing for sizing a dust collection system, which could use ducting work. I just chose to use steel piping because it was easier, but I showed you how to use rectangular ducting. You would simply open up a single pipe and then just go in there and change the material. Well, first you would, well, this is not going to let it do it now because it's already sized, but you would change the geometry to rectangular ducting, and then that's where you can do your duct width and your duct height, or you can do a custom pipe material database. If any of you want to try out any of our software products and you don't have them yet, or you want to try, if you have Fathom or Arrow, but you don't have the ANS module yet and you want to give it a spin, then please feel free to contact us. If you're within the United States, contact us and we'll set you up with an evaluation license. That way you'll be able to try out the capabilities yourself. If you are outside the United States, then please contact your local channel partner, whichever country that you're in, find your local channel partner and contact them, and they'll be able to be happy to set you up with an evaluation as well. Thank you all very much for your time today. Take care and have a wonderful rest of your week.